Okay, so here we are with part 3 of IS number 14. This is about actually constructing confidence intervals for P, the population proportion. So the question is, which way will the Hershey Kiss land? And I love teaching this lesson in class, so we get to have Hershey Kisses. It's great fun. But of course, we're not in class, so we're just going to talk about it. Our reference for Hershey Kisses is that when you toss a Hershey Kiss, it sometimes lands flat and sometimes lands on its side. So what proportion of tosses will land flat? And when you try this, it's not perfect, so it doesn't happen all that often. I would say it happens less than half the time. But I would normally have each group of 4 select a random sample of 50 Hershey's Kisses. I'd have a big bag, you'd select out 50, that would be your random sample, which of course the random sample is going to be important to us. We're noticing 50 is now going to be our N. To bring back to your desks, you're going to toss those 50 kisses and then calculate the proportion that land flat. So you'll take your total number that land flat and then divide by 50. P hat will be the proportion of kisses that land flat. Of course, it has the hat because it is the sample proportion. So before we move on, I'm actually going to emphasize that one more time. P hat is my sample proportion, right? P for proportion. And normally I would use a Greek letter to indicate the population proportion, but the Greek letter for P is pi, right? Pi, we just had Pi Day back on March 14th. And of course, we usually use that to represent the number 3.14, blah, 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 right? So we don't use pi in statistics to mean population proportion. Instead, we just use the regular P for population proportion, which then means our sample needs to be something more than just the regular letter P. So we put this hat on it. I know it's confusing, but we will get used to it. Okay, so that's why we use P hat. It's the sample proportion. So let's say you did this. I'm using just some data from a class I did last year. So your point estimate, right, would be your sample proportion. So to find your point estimate, you would use your P hat value, and I got 0.44. Okay, so let's see. 0.44, if I'm looking at what that would be with respect to 50, 0.44 of 50 would be 22. So that must have meant I got 22 out of my 50 candies to land flat. Okay, so now it's asking us to identify the population, the parameter, the sample, and the statistic. You won't be asked to do this every time explicitly, but as you start each of these confidence interval problems, you should think about these things to make sure that you are moving forward the right way. So first of all, our population, let's think. We're going to try to figure out the proportion of Hershey's Kisses. In general, Hershey's Kisses. So we're talking about all Hershey's Kisses. Obviously, we cannot figure this out for all Hershey's Kisses, which is why we're using a sample. And our sample is those 50 Hershey's Kisses that you would have been able to select were we in class. All right, so then the parameter is what we're interested in, right? We can't take averages of Hershey Kisses, right? So we're going to take proportion, the proportion that land flat. So P, remember, is the population proportion. It's the true proportion, which I'm going to abbreviate proportion, that land flat. Whereas P hat is just a little bit different from that. It's not the true one. It's the sample proportion that land flat. And of course, for us, we actually know what that sample proportion is right now. It's P hat, which was for us 0.44. Okay, so our next question is, was this sample a random sample? And why is that important? So I do want to warn you that all of these questions here are going to help lead us into what we need to know to make these confidence intervals. So one thing we have to know is whether the sample was a random sample. Yes, it told us that it was a random sample. And then why is that important? So if you remember way back to chapter 1 when we talked about sampling methods, it was important to have random samples so that we had a good representation of the population. And if we do have a good representation of the population, we can then generalize from our sample to the population. So we can generalize to the population. So we're going to use our sample data and generalize that to the population, but again, only if we have a random sample. Okay, so then it says, what is the formula for calculating the standard deviation of the sampling distribution of p hat? And at this point, you're like, oh my gosh, what? And I get that. So this is something that had we covered section 6.4 in your textbook, we would have talked about, but we really didn't have time. We moved on. So I'm just going to tell you what this formula is. It is standard deviation, right? So that is sigma. And it's a sampling distribution. That makes it sigma, not S, of p hat. So it is sigma sub p hat. Sigma sub p hat. This is like our sigma sub x bar that we dealt with in 6.5. Okay, so sigma sub p hat is equal to the square root of this fraction, and it is going to be p hat times q hat divided by n. Oh, I'm sorry, not hat. P times Q divided by N. The P hats and the Q hats will come later. So I can remember P stands for the population proportion and Q is 1 minus P. We talked about P and Q, remember when we were doing the binomial distributions, and that's gonna come up for us next. So it says, what condition must be met to use this formula? Has been met. Of course, we have not talked about the conditions, but again, this is from 6.5. So we have to have a binomial setting. And you've probably forgotten what it takes to have a binomial setting, but we asked those, we looked for those conditions bins, that it was binary. It could either be one thing or the other, right? There were only two options. It had to be independent trials. You had to have a set number of trials, and the probability had to stay the same for each trial. Now, usually the tricky part of that was the independent part. And so because of that, we talked about that 5% guideline, but really we normally talk about the 10% condition. We broaden it a little bit now that we're actually talking about confidence intervals. So the 10% condition means that we are going to check that our sample size of 50 is less than 10% of the whole population. So less than 10% of all kisses. We're checking that right now. So I think, let's see, 50 to be less than 10%, it'd have to be, 500? 50 is 10% of 500, right? 50 out of 500, let's make sure I'm right. Yeah, 0.1, okay. And there are definitely more than 500 Hershey's Kisses in the world. So 50 is definitely less than 10% of the population. And in general, our samples will be less than 10% of the population, so this condition will be met. So I'm putting a check mark to indicate that I did check that. I guess I should have put up here that yes, check, this sample is random. That's our first condition. Now we have our second condition. I want to emphasize real quick on here before I forget that again, these two questions, come from section 6.4 in your textbook. If you want to look them up, you can. I don't think it's necessarily worth your time, but if you wanted to, you could. Okay, so then let's talk about the next part. It says we don't know the value of P. That is the whole point, right? We are trying to estimate the population proportion. We don't actually know what it is. So instead, we're using P hat to estimate it, which means we're going to need to use P hat in this formula for standard deviation. So it asks us to calculate that. So I'm not going to write sigma sub P hat because this is actually going to be called something a little bit different, but I am going to plug into the formula. Again, we're using P hat now times Q hat divided by N. Told you those hats were coming in eventually. So let's remember P hat is actually 0.44 for us. So that makes Q hat 1 minus 0.44, which would be 0.56. And we also had that N was equal to 50. Okay. So let's plug in. So we have 0.44 times 0.56, all divided by 50. And then we have to take the square root of all of that. So the nice thing is that we can type that whole thing into our calculator. We start with the square root, second, and then the x squared key gives us that square root, that key right there. Okay, so then we have 0.44 times 0.56, and we're dividing by 50. Oop, I did forget my times. I'm just gonna hit the second insert key, and that allows me to insert my times. Okay, there we go. So I get 0.0701, et cetera. I'm going to round it to 4 decimal places. So I have 0.0702. Okay. And then it says, would it be appropriate to use a normal distribution to model the sampling distribution of p hat? Oh, again, you're like, what? I don't know. So we had the central limit theorem to tell us whether or not we could use a normal distribution to model the sampling distribution of a sample mean of x bar, but that doesn't apply for sample proportions for p hat. So this also comes from another section in your book that we didn't cover. This is from section 6, I believe. Oh, no, sorry, 6.7. Don't want to get that wrong. 6.7 is about using a normal distribution to approximate a binomial distribution, which it's not all that useful anymore, so we just didn't use. But if we had gone back and talked about it, we would have been able to see the sampling distributions. So there's just a simple condition that we need to check. I'm going to call it the large counts condition. Your book doesn't really have a name for it, which I feel like is especially unhelpful. So I'm going to give it a name. But it does ask you to calculate these same things. That n times p hat, right? So the sample size times your sample proportion, which is basically your number of successes, right? Your number that actually flipped. If we do 50 times 0.44, I did this earlier, we get 22. Okay, so automatically I know if 22 of them landed flat, I shouldn't have said the number flipped. This is the number that landed flat. 22 of them landed flat. That means 50 minus 22, or 28, did not land flat. They landed on their side. So the other calculation you have to do is that n times q hat, or 1 minus p hat. So this would be 50 times 0.56. And if I do that, I'm pretty sure it's going to be 28. 50 times 0.56, yes, it's 28. So that's the number that landed on their side. Okay, so what we have to check is that they are greater than or equal to 10. And that's true. All right, so to answer the question, yes, it is appropriate to use a normal model. Okay, and that's good news for us because the next page is going to ask us to use the normal model a whole lot, and we've already been learning how to use it. Okay, so the other thing that I want to say before we move on from this page, as we move forward, we're going to talk about the 3 conditions we have to check. This is condition number 1. Condition number 1, okay? Do we have a random sample? Then we will have to check this 10% condition. This is condition number 2. We'll have to make sure that we have a binomial setting. The main check there is whether or not it's independent, and it will be independent if our sample is a small enough portion from the population. I actually don't know if I explained that well enough the first time. I'm going to say it again one more time. Remember, that was because of sampling without replacement, right? We're choosing these 50 Hershey cases and we're not replacing them. So technically, they're not independent from each other, but if our sample is a small enough portion from the population, then the differences in their probabilities when we sample without replacement compared to with replacement is so small that we can just go ahead and act as if it is with replacement so that they are independent. Okay, so then the third condition is this large counts condition. So this is condition number 3. And actually, I'm using this word condition, and looking back, your book uses the word requirement. Condition, requirement, same difference. Okay, so those are the 3 conditions that we will have to check. All right, so let's move on to the back. We have some more calculations to make. Okay, so this says in a normal distribution, 95% of the data lies within blank standard deviations of the mean. Well, let's use that 68, 95, 99.7 rule. That tells us that 95% lies within 2 standard deviations of the mean. At least that's what our rule tells us. That value is called a critical value. So we're going to use table A, or the inverse norm function, to find these critical values. Instead of doing 95%, let's go ahead and do 80% first. So let's draw a quick picture over here. I'm talking about my standard normal curve. So the center is 0, goes out 3 standard deviations in each direction, right? Okay, so I'm talking about 80%. I know that's at least more than 1, but less than 2. So maybe like this much is 80%, okay? I guess I should instead say 0.8000. So I could look for that amount in my table A, but that wouldn't be right because this isn't necessarily a left area. The left area that I would be looking at would be all of this, right? I want to find that z-score that bounds this area. So it'd be the 0.8 plus this 0.1 over here for a total, I should say 0.8 plus 1, for 0.9. So I'm really looking for 0.9 in table A. Okay, so let's look for that. 0.9 is definitely going to be on the positive z-score side. I see 0.8925. I'm going to keep going up. Oh, 0.8997, 0.9015. Okay, so 0.9 would be somewhere in the middle here. I'll try to get closer so you can see that a little bit better. 0.9 would be somewhere in the middle here, but 0.8997 is definitely closer. So I follow this out to find the z-score. Follow it out. I see 1.2, so it's 1.28. All right, 1.28 is my z-score there. 1.28. All right, so I can do that again for the 90%. So now I'm going to sketch another quick picture, and these are like tiny little pictures. I apologize, they're not super accurate in scale. So there's 0, 1, 2, 3, 1, 2, 3. Okay, again, 95% is between -2 and 2, so 90% is going to be even closer to those two, right? Kind of a similar picture to 80%, just a little bit more expanded. So that's my 90% or 0.9. But again, I have to include this little area out to the left as well, right? All of this is what I'm interested in. So let's think. If the middle is 90%, then the outside of 90% is 10, but it's this half and this half making up that 10. So this half is only 5%. So I have a 0.05 plus my 0.9 in the middle. That's what makes up my red portion here. I guess I should put that in red. The 0.05 on the very left tail plus the 0.9 in the middle. Okay, so that would give me 0.95. Oh, I've looked for 0.95 in table A before, I believe. Let's see if I can find it. Nope, that one. There we go, 0.95. Of course, it's right between 0.945 and 0.9505. So I follow that little star down. An area of 0.95 is one of my special cases, so its z-score is 1.645. All right, so 95% of the data lies within 1.645 standard deviations of the mean. Of course, I should have explained that a little bit earlier. I'm looking for the z-score because the z-score is the number of standard deviations from the mean. So I'm finding this z-value here, and 1.645 is my z-value there. Okay. So let's do another one. 95% of the data now, so I'm drawing another picture. All right, so 0, 1, 2, 3, 1, 2, 3. Now 95% I thought was 2 to 2, right? I thought that's what it says for my 68, 95, 99.7 rule. Ooh, my curve was definitely not very symmetric there. That's all right. Okay, so again, it's not just 95%, it's the 95% plus that little left tail area. So, okay, let's think. 100 minus 95 is 5. The 5 is split into two pieces. 5 divided by 2 is 2.5%. So 0.25 plus 0.95. Let's see, that would be 0.975. Okay, so now I look for 0.975 in my table A. 0.975. I see 9598, 975, go back to the next row, 9756, getting close. Oh, it's exactly there, 0.975. So that is at 1.9, and follow that all the way back up to the top, 0.6, so 1.96. All right, so it turns out it's not actually exactly 2, it's 1.96, but of course 1.96 is pretty darn close to 2. Okay, so one more, and the reason that we're doing all of these right now by hand is so that they're recorded for you for later. Whenever you have an 80%, a 90%, a 95%, a 99%, you can come back here and look at this, right? You can calculate them again on your own if you want to, but these are pretty typical values that you can use for the future. Okay, so 99%, remember all the way out to 3 standard deviations from the mean is 99.7%. So this is just a little bit less than that, right? We're not going all the way out to 3 standard deviations, but close. I guess I should make that a little bit more clear with this side of my curve. Let's make this not hit the axis so soon. It's 1, 2, 3. Okay. So again, we're going all the way. The 99% plus that tiny little bit that's not included. So let's see. This is my 99%. Looking for that C-score. So this is, okay, outside of 99% would be 1%. Half of it's on over here, half of it's over here. 1% divided by 2 is half of a percent. So that would be 0.005 plus my 0.99 for a 0.995. That's what I'm looking at. Okay, I'm looking for 0.995 when I look into my table A. All right, 0.9948, 0.9949, 0.9951. Okay, so 0.995 is exactly between those two. I follow that down. This must be a special case. Yep, there it is. Area of 0.995 is 2.575 for a z-score. Whew, okay, 2.575. Whew, that was a lot of work, but now I have them recorded. These are my critical values. That is a new vocabulary word, critical values, for each of those different competence levels. Okay, so I do want to introduce to you this new notation, of course. It mentioned this back in section 6.5, I think, back in chapter 6 somewhere, but I kind of skipped over it because it wasn't relevant yet, but now it's relevant. So in your book, now in chapter 7, they're using z sub alpha divided by 2 to indicate a critical value. I just don't really like that notation. It's clunky, and alpha divided by 2, what's alpha stand for? They're using alpha a little bit differently than they did in chapter 6. I just don't like it. So I'm going to go with what we used when I was teaching this previously, z star. Just with an asterisk. The asterisk means that it is the critical value. So each of these are critical values depending on the different competence levels. Okay, so whenever you see that z sub alpha over 2, kind of replace it with z star in your head, right? It makes our formulas just look way too clunky to use that. Okay, so it's asking us to calculate the margin of error for a 95% interval, and it's telling us how to do it by multiplying the critical value and the standard deviation you found. Okay, so I have to show my work. I need to remember what kind of confidence interval am I even trying to make here? Let's see. Did I ask us exactly? Oh, it did not ask us. So we get to choose our own. Oh, no, it does. It says right here. Sorry. Calculate the margin of error for a 95% interval. That's pretty important. So the 95% of interval tells us which critical value to use, right? We came back up here. 95% has 1.96 as its critical value. So we'll start with that. 1.96 times, and then the standard deviation we found on the previous page was that 0.0702. 0.0702. Okay, so if we multiply that out, let's check that out real quick. 1.96 times 0.0702, I get 0.13759. I'm going to round that to just 3 decimal places, let's say, so 0.138. Okay, now it's saying find the 95% confidence interval using point estimate plus or minus margin of error. Okay, I have my margin of error, right? This is E, this is my margin of error. My point estimate was my p hat from the previous page, remember? That was the p hat was 0.44. So let's write this out. It's going to be 0.44, the point estimate, plus or minus the margin of error, 0.138. And of course, I actually have to add and subtract, so I'm going to do that. I don't think I have to write it out. Hopefully you know that I'm going to subtract first because I want the smaller number first. So I'm going to do 0.44 minus my 0.138 first to get 0.302. So 0.302, comma, and I'm going to add the other number, 0.44 plus 0.138. So I should say I'm going to add to get the upper limit. So point estimate plus the margin of error, 0.578. 0.578. All right, I've done it. I've constructed my first ever confidence interval. All right, so then it asks us to add our interval to the graph on the board. Of course, we don't have a bunch of different intervals like we would in a normal class. So I'm just using some examples from last time. Here's my number line, right? Possible proportions. Here's my actual interval, right? It goes from 0.2, all the way up to 0.578. So somewhere in there. And then I'm making a dot for the actual point estimate this comes from. So from the 0.44, there's my point estimate, okay? Now these other intervals were intervals from other groups in the class that I had last year. So some of them had something as low as like 1.5 up to 1.4, something like 1.22 up to 1.5-ish, something like 1.2 to maybe 0.49, okay? Different confidence intervals that showed up based on the different sample proportions that students got on their 50 Hershey's Kisses. So the next question is, what do you think is the true proportion of kisses that land flat? So I look at this and I see, all of my intervals have this same general area that they're hitting, right? It looks like between 0.33 and 0.44. Definitely 0.35 is in all of them. So I would hazard to guess that P is about 0.35, right? Now, that's not a true point estimate, right? I don't in general make estimations like that. I really want to stick to my interval, but if I had to, I could make a guess for what the true proportion is there. Okay, so that's our first confidence interval. We're going to take some big ideas on that and then actually work one out with all of these guiding questions for us in our next set of notes. I'm sorry, not in our next set of notes, in our next part, in part 4. But I do want to come back and hit on some important points. So first of all, I want you to notice that this margin of error for a 95% confidence interval uses that that critical value, which is essentially a z-score of 1.96, really close to 2. Remember when we were calculating those min and max usual values? Right? We had to add 2 standard deviations and subtract 2 standard deviations. That's what we're doing here. Round 1.96 up to 2 times the standard deviation. Just the exact same idea. So that's where we get the 2 standard deviations for the min and max usual values. 95% confidence level is pretty common. The other thing that I want to point out on here is some formulas. So our margin of error formula, I'm going to go ahead and actually write out the words. Margin of error. Error is actually equal to that notation E. So we find that, again, by taking our critical value. And again, I'm using words because I think the new notation can get a little bit confusing at first. So our critical value times your standard deviation. Okay, and I'm going to introduce a new notation for standard deviation, of course. It's not your technical standard deviation. It's actually your standard error for P hat. Oof. I better go back. I don't think I pointed that out on the previous page when I meant to. So I put SE instead of SD for standard deviation because when we wrote down this formula, remember, we don't actually know P. We had to use P hat to estimate it. So this is really the standard error for sample proportions, right? S sub E stands for standard error. And I guess I will actually write out what that stands for. So standard error. Instead of standard deviation. Okay, so let's flip back over to our formula. The margin of error, again, is the critical value times the standard error for the sample proportion. And we usually use Z star to indicate a critical value. So you may see this formula as Z star times SE, the standard error for the sample proportion. And of course, your crazy book uses this Z sub alpha divided by 2 instead of Z star. So I'm sorry if it's confusing that I'm introducing a new notation. I just really hate that Z sub alpha over 2. Okay, so then we had our confidence interval. I'm also going to kind of give you a formula for that. So this is our point estimate, right? We know a formula for confidence intervals. It is, let's go all the way back to the first big ideas. a point estimate plus or minus the margin of error, and we said p hat plus or minus e. We actually know how to calculate margin of error now. So p hat plus or minus my z star times the standard error, which of course we have to know a formula for the standard error, so I might as well just plug that in here. So times the square root of p hat times q hat divided by n. Okay, there is our formula for a confidence interval. Confidence interval for a sample proportion, of course. We'll learn about means later. All right, I think that is all that I wanted to add as far as like little notes. Oh, one more thing that I will add about being able to calculate these critical values. We could have done this in our calculator. We would still kind of need this picture to help us figure out what area we're actually interested in. But if we had wanted to, we could have used the inverse norm function with an area of 0.9, a mean of 0, and a standard deviation of 1, because this is the standard normal curve. Remember that inverse norm function is in second distribution or second bars, and you scroll down to inverse norm. Oh my, I hit the wrong button again. Sorry about that. Inverse norm. Tell it 0.9 for your area, mean of 0, standard deviation of 1. And there you go, 1.2. And actually gives us a little bit more specific. It says 1.215. Let's round that to 1.28. I actually want to get the most specific value we can in there. So I'm going to go ahead and do that for all of these. This would be 0.95, right? That was our left area. Mean of 0, standard deviation of 1. Obviously, all of this writing will be the same except for the area, so I just want to fill those in. 0.975, 0.995. Okay, so let's go ahead and calculate those. I'm going to just go up and select the inverse norm function since I've already done it. So now I want 0.95, comma 0, comma 1 for my command. All right, 1.6448, so 1.645. That makes sense. That's why our table is more specific. There's a special case. Okay, so now for this next one, I want 0.975. So 0.975, comma 0, comma 1, parentheses, and I get 1.9599. If I round up, that's where I end up getting this 1.96, technically 1.960. Doesn't really change my calculations. And then finally, let's do the 995. So that's just one number to change, 995 for 99%. Oh, okay, I get 2.5758, which is where they give us 2.575. Yeah, okay. All right, so that is it for our first ever confidence interval. Check back with the next video to see the big ideas and check your understanding.